In this section of chapter 21, I would like to discuss about detection of radioactivity, nuclear binding energy, critical and supercritical mass. Here we are going to discuss detection of radioactivity by using film badge. Radiation leaves its mark just like X-ray leaves its mark on a film. The greater the extent of exposure to radiation, the darker the area of the developed film. So by looking at that developed film, scientists can get an idea what kind of exposure of radiation someone had. In that case, you need to wear film badge when you work in with radioactive substances. Geiger counter is the most popular detection device of radioactivity. It has a cylindrical container that acts as a cathode and is filled with argon. So you can see here the argon within the cylindrical container. And the central rod acts as an anode. Since the container has argon, whenever any radiation enters into that chamber, cylindrical chamber, or cylindrical container, then it knocks off electron from argon, and argon becomes plus, and electron is knocked off. Now, since one of the plate, like cathode plate, is negative, and anodic plate is positive, keep this in mind. This is not a voltaic cell, so that's why sign convention is just the opposite, and is determined by the battery or source of voltage used from outside. So whenever argon plus sees the negative plate, negative cylindrical plate, it's attracted towards that plate, and electron is attracted to the positive plate, and then there'll be burst of electricity, and that provides a signal. So each time ionization event takes place, there'll be a signal, and that's how we scientists know how many of these how many of those energetic particles entered into this chamber, cylindrical chamber filled with argon. Scintillation counter. In this device, there is a plating of phosphorescent material like zinc sulfide, for example. They're light sensitive. Whenever a gamma radiation or energetic radiation strikes the plate, like with zinc sulfide, it gives off light, and that's amplified and then counted. So each time one of these radiation would hit that phosphorescent plate, you'd expect light to emit, and that's how we know how much of this radiation has fallen on this zinc sulfide plate, and that gives an idea of how much exposure that somebody who worked in the radioactivity lab had. Here I'm going to show you how to calculate nuclear binding energy, and then we'll explain to you what nuclear binding energy means as we do this calculation. So the information that is known is helium mass, which 4.00150. You do need that many significant figures because you see a very small mass difference. Now, individual proton weighs 1.00728, individual neutron weighs 1.00866. So there is a small difference in the weight of proton and neutron, but both are pretty close to 1. Since we have 2 protons, so two times that value, and 2 neutrons, so 2 times the value of separated neutron or isolated neutron. When you add these masses, the total mass is 4.03188. But keep in mind that helium has 2 protons and 2 neutrons. Then if this is helium, has 2 protons and 2 neutrons. The question is, when we add masses of isolated protons, 2 protons and 2 neutrons, that mass is greater than the mass of helium. So in other words, when you make helium nucleus from 2 protons and 2 neutrons. Let me show you hypothetically. Proton plus neutron plus neutron. When you make helium, this is helium 2 4, the mass on the right hand side is greater than mass on the left hand side. So what it means is, as these 2 protons and 2 neutrons are combined in a small nuclear volume, a part of the mass disappears, and we call it mass defect. So by subtracting these masses, you're going to get 0.03038 atomic mass unit. According to Einstein, whenever there is a situation like this, that mass that seems to have that mass defect had happened, or the mass that seemed to have disappeared, is actually converted into energy, and it is given by delta m times c squared, basically mc squared, mass defect times velocity of light squared. So here we are showing you the math from atomic mass unit to gram. Conversion value is Avogadro's number, 6.022 times 10 to the power 23 AMU makes a gram, 1000 gram makes a kilogram, and then this is c squared, velocity of light squared in meter per second. So basically our unit is kilogram meter square per second square, and that's joule. So we get 4.533 times 10 to the negative 12 joule, and that's considered to be the binding energy. So whenever you have isolated protons and neutrons, bring them close together in a small nuclear volume, and you create helium, a part of the mass is going to disappear and it forms energy, and that energy is given off, and that holds all these protons and neutrons together, and that's called binding energy. The binding energy per nucleon is given by 4.533 times 10 to the negative 12. That's binding energy divided by the total number of nuclear particles, which is number of protons plus number of neutrons. In case of helium, there are 2 protons and 2 neutrons. So there are 2 protons plus 2 neutrons, and that makes 4. So that means per nuclear particle, the binding energy will be given by the value that we got, 4.533 times 10 to the negative 12, divided by 4. Now, in this graph, you're looking at how nuclear binding energy changes in both fusion reaction as well as fission reaction. Fusion reaction tells us when you have lighter nuclei, if you fuse them together, there'll be a large increase in binding energy. Like if you look at the left-hand side where fusion has happened, if I have, say, 2 hydrogens fused together to helium, there's a sharp rise in the binding energy because this axis is binding energy. So fusion reaction, when 2 lighter nuclei are fused together, there'll be a large increase in binding energy per nucleon. On the right-hand side, you're looking at fission reaction. Fission means large nuclei like this, large nucleus of, say, uranium-235. Say uranium-235 is broken down in 2 big chunks of masses. If tiny bit of mass comes out of uranium-235, it's not considered to be fission reaction. So it has to be 2 big chunks of masses. And if that happens, you see there'll be a sharp increase in binding energy per nucleon. So that's what we are pointing out here. In fission reaction, a heavy nucleus splits into 2 large masses with large increase in binding energy. Now here we're going to explain large increase in binding energy means large emission of energy and greater stability for the nucleus. And with a simple analogy, I'm going to explain that to you. You're seeing 2 figures here, figure 1 and figure 2. Figure 1 indicates a large binding energy. Why? If you look at figure 2, you'd understand why figure 1 increases it provides information about large binding energy. Figure 2, the bird is trying to fly away and you are trying to hold it. It will be really hard for you to hold it, so you have a smaller binding energy because it's trying its best to fly away from you. On the other hand, in figure 1, the bird got tired. It doesn't want to fly away anymore. It lost its energy before it got to this stage. So this is the case 1 had a greater energy loss, and there is a greater stability and hence a greater binding energy. That's the figure 1. Both fission and fusion reaction involves increase in binding energy and hence a release of large amount of energy. So always when there is an energy loss and there will be greater stability, so increase in binding energy goes with release of large amount of energy. In this slide, you're looking at fission reactions. Even though you begin with same uranium-235, so uranium-235 nucleus, but we're getting several different products. Neutron acts like a bullet because that causes this breakdown of this nucleus. First, temporarily, it goes inside and makes 236 because neutron mass is added here. 236, then that 236 breaks down. Let's make it 236 now. 236, and it can break down in several different ways. So one could be like this, another I'm going to use a different color like this. So there are a number of possibilities, and that's why you have variation in the product formation. In each case, quite a bit of energy is given off because remember that I've shown you that graph which shows that in each time a fission reaction happens and you get two chunks of masses, binding energy is increased, and binding energy, increase in binding energy goes with emission of energy. Here I want to emphasize that this is not a fission reaction. Why? Only tiny mass come out of uranium nucleus. So this is uranium. If a tiny bit of mass comes out of this, that's not fission reaction, and you're not getting much energy out of this. Now, what is the critical mass? This is the amount of fissionable material that must be large enough to maintain a chain reaction with a constant rate of fission, and I'll explain that to you. Now, if you remember that when I have given you a number of fission reactions, in each case you had more than one neutron as the product. Now let me show you how neutron can be effective in causing the second, third, fourth reactions. Let's assume that on an average, out of two neutrons that comes out, one of them would be used in breaking the next nucleus, but the other one would be lost. If that is the case, then look at here. The first neutron is going to split this molecule, and the two neutrons are coming out. Then one of them would be lost. The second one is going to again split this nucleus, and again one is lost. The other one is available. So this would keep on going, and this is called a chain reaction. And this kind of chain reaction is important in power production, where we can control the energy production. And for that you need a critical mass. Supercritical mass is larger than a critical mass and allows more than one neutron to cause fission reaction, and there will be multiplicative chain reaction. In next slide, I'm going to show you how that works. Here you have one neutron coming in, and then striking this uranium-235, say it will split, and it will give off, say, 2 neutrons, and this time both neutrons are effective on an average. So if you look at this, again, this neutron coming out is going to split this nucleus into 2. The other one is also going to split that into 2. So as time goes on, the chain reaction increases in a multiplicative manner. Initially you had only 1, then you have 2, and then you have 4, and so that's how it multiplies. And each time fission reaction happens, quite a bit of energy is given off. So in a multiplicative chain reaction, huge amount of energy is given off within a short amount of time. And that's the explosive reaction that would take place. It would go on in an uncontrolled manner. And this is used in atomic bomb. Hiroshima bomb was about 20-kiloton bomb, but recent days bombs are 20 megaton, about 1,000 times more powerful than Hiroshima bomb, Hiroshima and Nagasaki bomb dropped in Hiroshima and Nagasaki in Japan.